All right. My name is Sarah Hilliard, and I'm going to be presenting my undergraduate research on fatigue and cyclic loading in aircraft engine turbomachinery that I've been doing with Dr. Wayne Strasser at Liberty University. So first up, a brief introduction of some aviation and aerospace engineering type topics. First of all, gas turbine engines are the most common type of engine used in aviation. They're typically found in planes and in helicopters, and they are made up of rows of fan blades in compressors and turbines. So these fan blades are exposed to vibrations due to unsteady flow, as well as axial and centrifugal strain. The blades are also exposed to high levels of fatigue from those vibrations, unsteady flow, etc. And the two types of fatigue that they experience are due to cyclic loading and thermomechanical fatigue. So thermomechanical fatigue is going to be when you have cyclic applications of hot and cold temperatures on a piece of material. When it goes from hot to cold and has extreme temperature gradients, it can cause fatigue to actually occur in the material. That is not the main topic of fatigue that we're going to be covering today, but it is worth mentioning. So we're going to be talking about cyclic loading. And the reason why fatigue prediction is so important is because predicting fatigue allows us to prevent failure, and it can also help us to engineer better components and engineer better materials to make better components. So the second half of this topic has to do with some material science concepts. First of all, metals are crystalline solids. This means that they are made up of crystal units that are stacked together. The crystal units are typically body-centered cubic, face-centered cubic, or hexagonal close-packed. There are a few other types that occasionally occur, but these are the three main types that regularly occur. So due to atomic defects, separate crystalline units develop in a material, and we call those crystalline units grains. So this image here is going to give you just a brief understanding of how grains develop. On the left, you can see a bunch of orange squares lined up together to create these larger shapes. If you imagine that each of those orange squares is one of these crystal unit cells that are either BCC, FCC, or HCP, as we talked about above. They are lined up together to create these larger crystalline units, but they don't line up exactly with the ones next door. So separate units develop, and those are the grains. And then on the right is how the grains from the left would look actually under a microscope. The black lines on the picture are the grain boundaries, and those are a really important area in terms of the strength properties of a material. So how do these two things connect? Well, first of all, fatigue affects materials on a microscopic scale. So it affects the grain structure of a material. But the grain structure of material also affects how it experiences fatigue. So the size and orientation of the grains in the material change how fatigue occurs. And this happens in a cycle. So as fatigue is occurring, it's changing the grain structure, and the grain structure is, of course, dictating the way that fatigue is experienced. So to sum up, unsteady flow causes vibratory loads in turbines, and these vibrations cause fatigue. The microscopic scale of fatigue is often overlooked, and it's hard to find distinct correlations between grain angles and orientations and sizes and the actual fatigue life of a material. So it's really important to understand what's happening at the microstructural scale of a material in order to understand how it's experiencing fatigue, and therefore engineer better materials, understand when it's going to fail, and predict it more accurately. So the goal of this research process was to validate the use of an analysis tool in ANSYS to simulate microstructure, to investigate expected vibratory loads caused by unsteady flow in a gas turbine engine, to model engine turbomachinery for analysis and apply typical mechanical properties for an aviation grade material like titanium that turbine blades would actually be made out of. So then we could take this piece of turbomachinery that we have modeled and applied these mechanical properties to, and actually applied the vibratory loads that we found in the second step to that piece of turbomachinery. At that point, we could observe microstructural changes due to fatigue loading and draw conclusions about the fatigue life of turbines. That sounds pretty cool, right? Well, let's talk about how the process actually went. Our first step was to validate the use of a simulation tool for this application. The tool in question was the crystal plasticity tool in ANSYS. So the hope of this portion of the research was to both validate the tool and simultaneously learn how to use it. So ANSYS Innovation Space provides a certain number of instructional courses for some of their tools that can teach users how to actually use them properly. And so we decided that it would be ideal to follow along with this course that was given on an official ANSYS website to simultaneously benchmark our results versus a published or established value that actually came from ANSYS to make sure we were getting reasonable values, and at the same time learn the process for how to go through meshing of a microstructure, how to set up and actually solve this type of a simulation. So that should be pretty straightforward as well, right? Just follow the process. Unfortunately, it didn't end up being as straightforward as we hoped. So I'm going to take you through the actual process for trying to validate that tool. First up is meshing the microstructure. Now, meshing is an extremely important part of any simulation, but it is especially important for meshing a grain structure because it has to be done super carefully. Intergranular contacts can dictate the properties of a material. So since we are meshing on such a small scale, we have these separate units that are grains actually in our mesh. And it could be problematic if the individual grains were meshed as separate units and not as one large unit with proper contacts set all throughout. It could result in the load not being applied properly. So this course that we were following along with gave two options for mesh elements, hexahedral mesh elements and unstructured tetrahedral mesh elements. The meshing for the crystal plasticity tool in ANSYS is done using Python. Pre-processing scripts and conversion scripts were given to take the grain data and convert it into a file type that ANSYS actually can readily accept. So we started out first with the hexahedral meshing option. We did the file conversion with a Python script that was provided by the course. You can see it on the right there on the screen, and imported it into ANSYS after the file conversion in Python. However, there was a problem. The data file that we were given did not include the correct number of data points to actually create a hexahedral mesh. So you can see a little bit closer up of the mesh that was created here. It looks a little bit like Swiss cheese, and we know that's not what hexahedral mesh is supposed to look like. We actually encountered the error with the data file in the process of trying to do the file conversion in Python. There was an if-else condition in the Python script that told it to stop running immediately if the correct number of data points were not found. And of course, there were not enough data points. So we struggled for a while trying to find out why the Python script wasn't running, only to find out the data file was incorrect. We did try to make the mesh anyway. As you can see, we have images of the mesh on the screen. Just kind of to see what would happen to try to follow through with this approach, since it wasn't possible to manually add points to the grain data file. We just tried to continue moving forward with this process, just kind of to see what would happen. So obviously that was not a successful mesh. However, we decided to go forward with unstructured tetrahedral mesh elements, since that was another viable option that was outlined, and it should be another possible way for us to complete the simulation. So the first step was to set up a dummy geometry in ANSYS and mesh it using beta mesh workflows, and then to generate the mesh using a microstructure meshing template. There are actually certain templates that are available with an installation of ANSYS that you can navigate to and use them to create a mesh. So a microstructure meshing is one of them. We then converted to the desirable ANSYS input file format using a Python conversion script. It was different from the previous one, but of course the Python script was not the issue in the hexahedral meshing option. It was the data file that we were given. So after we opened this file in ANSYS, we found this lovely, lovely, successful unstructured tetrahedral mesh with 15,200 linear elements. It's a 1 millimeter by 1 millimeter plate that's about 0.02 millimeters in depth. And you can see a lot of different colors on that mesh. Each color represents 1 grain of the material. So there are 9 grains in our 1 millimeter by 1 millimeter plate of aluminum 2024 T3. So since we were able to successfully create the mesh, we proceeded to material assignment, which is also done via Python using that same initial pre-processing script from the hexahedral meshing option that was given by the ANSYS Innovation course. The really great thing about doing material assignment via Python is that it can be adapted to any material provided you have the crystal plasticity parameters, like the crystal type, the slip resistance, the linear hardening modulus, etc. If you have those parameters, you can just put them into the Python script and get the material assignment parameters for any material. So we added the material assignment parameters to ANSYS through an APDL command and proceeded to the boundary conditions. For the boundary conditions, we wanted to simulate plane strain conditions, doing a simple tensile test. So we set displacement boundary conditions on the piece and fixed the front and back in all directions, as well as the sides and the base. The only face that was allowed to translate was the top face, which is labeled face D in the figure, and it was given a displacement of 0.02 millimeters in the Y direction straight up. At this point, we were ready to solve, or so we thought. On the right there, you can see the contour plot that resulted from this solve attempt, where we have a maximum equivalent von Mises stress of 6.8 times 10 to the negative 10th megapascals. So effectively 0 stress is being felt by this 1 millimeter high plate being stretched by 0.02 millimeters. Our intuition tells us that can't be right. So we did a quick mathematical verification just to have, proof to aid our intuition that it was in fact not correct. So using engineering strain and engineering stress, as well as a typical Young's modulus for aluminum 2024 T3 of about 70,000 megapascals, we found that the engineering stress should be around 1,400 megapascals, which seemed a lot more logical than 0. So what now? Well, if at first you don't succeed, try again. And fail again, unfortunately. On the right, you can see a very similar stress contour plot to the one that you previously saw. This one has a little red tag marking the maximum stress over the whole specimen, and the maximum stress should be seen actually in red on the specimen, but that point of maximum stress is so small, you can't even see any red in the contour plot. So now that we have tried twice and failed twice, it's time to try something new. In terms of trying something new, we did some solution sensitivity investigations by changing the solver settings, changing the boundary conditions, and changing the material properties. In all 3 of these cases, the solution was still approximately 0. You can see on the right there, a maximum von Mises stress of 7.87 times 10 to the negative 10th megapascals is the maximum stress. So we know that that can't be right, and because the solution is not at all sensitive to changing the solver settings, changing the boundary conditions, whether it's 0.02 millimeters or 5 millimeters that this piece is being stretched by, the stress that it feels is no different, as well as material properties, whether it is aluminum, whether it's high carbon steel, whether it's copper, there's no difference in the maximum stress values, which we know is incorrect. So at this point, we found something very interesting, did extensive research and hours of scouring through every single step of the instructional process and repeating the entire process over and over, trying to find what the error could have been. So one of the discoveries that we made was that according to the instructional course, the geometry that is created should be one solid body. It is, yes, 9 units, 9 grain units, but they should all be combined into one solid body. However, when we followed the meshing procedure exactly, we got 9 solid bodies, not one. They were all combined in this solid bodies, quote unquote, under geometry, but they are 9 separate bodies. So it seems like it should be pretty straightforward to just set contacts between them and combine them. However, the geometry is fully set in the meshing process and in the Python scripts. So it's not actually possible to edit the geometry that we have of this test specimen. In terms of the future work that we have for this research, there are still a lot of the research goals ahead of us. So we have a few approaches for how we are hoping to still be successful in validating this tool. The first one is investigating the use of PyAnsys. The course from Ansys Innovation also outlined briefly how to code the same simulation using an entirely APDL command-based approach. This is an extremely complicated undertaking, but it is worth doing just to see if it would be successful. It is unlikely, but the hope is that it would eliminate the potential for errors going between ANSYS and Python back and forth over and over again. The second approach would be to use Dream.3D or electron backscatter diffraction to build a grain structure for another part. This would make hexahedral meshing an option, since we could make sure that we have enough data points to make that hexahedral mesh. However, it would not allow us to benchmark versus the tool, which was half of the hope of this step of the research process. Once the tool can be validated, if it can be validated, we can proceed with our research plan to apply cyclic turbulent in-flight forces, observe microstructural changes under fatigue, and draw fatigue conclusions. So in conclusion, we have been studying the use of ANSYS crystal plasticity for use with microstructural fatigue simulations. We encountered several issues in the validation of this tool, including a faulty data file that didn't include enough data points, faulty geometry that did not have proper contacts set, most likely, and all-around faulty results that were stress of approximately 0. Our next step involve investigating the use of PyAnsys and generating new grain structures to try and apply this tool. A quote that comes to mind often as I'm working through this research is this quote by Thomas Edison that says, "I have not failed, I've just found 10,000 ways that won't work." Sometimes in research, we feel as though we found 10,000 ways that won't work, and we just cannot find that way that will work. However, it is important to remember that part of research is failing sometimes, and a big part of research is continuing to move forward, to push forward, and to try and to search and investigate as we are feeling like we're finding 10,000 ways that won't work. So thank you so much for listening. This is a QR code that you can scan if you're interested in learning more about my research or what the Fluid Group at Liberty University does. Thank you again so much.